state it, they might not. But sometimes there are direct questions. I'm just thinking AP stuff. Sometimes there are direct questions from MBT, aka mean value theorem, and or roles. Remember, I wrote down yesterday, roles is the specific case. MBT is the general case. Let's talk about specific and general for just a second. Dog is a specific example. Mammals is a general category. Does that make sense? You guys think of another one, or I'll think of another one. Pumpkin spice latte is a specific example. Coffee or Starbucks menu is a general category. Does that make sense? Okay, think of another one. What's another specific?
Dog is general, golden retriever is specific.
Ooh, dog is general, golden retriever is specific. Good. What's another general specific?
Sadness is specific. Emotion is general.
True.
Good job,
True. Joy is lasting, happiness is temporary. Oh, wait.
I don't think that was specific.
Is happy really?
Is happy exactly the same? Happy and you know what's happy? No one else? Okay, so general specific. You guys get the idea of roles as a specific type. MBT is the general category, in a sense. Which means, this is actually really cool for you guys to know, even if something makes you think of roles, you can still always state MBT. You can't do it the other way around. So, we're going to work really hard on making sure that we get MBT, and then being like, oh wait, what's roles again? So, we started by writing down roles. He's the one that came first. We gave him credit where credit is due. He says, I can guarantee a zero of a derivative. He's not the only one that can guarantee a zero from the derivative. MBT and IBT put together in tandem can kind of prove it also. But he says, I can prove that the derivative has a zero when, blah, blah, blah. Okay? But MBT, what does he say? I know I'm personifying a theorem, but that's okay. What does it say? What does it guarantee?
A derivative that equals the average.
A derivative that equals the average rate. That's one way of saying it. That's one way of saying it. The instantaneous equals the average, the derivative equals the average. The other way of saying it is that the slope of the tangent line, it guarantees a derivative. The slope of a tangent line is the slope of a secant line, or the slope between 2 points, the two endpoints. So MBT guarantees that the derivative, now it's still specific in a way. Because, for instance, my dog and my mammal category, doesn't a mammal still have certain criteria to fit under? It's not like the entire animal kingdom, or any living thing, or, okay, you can keep on getting more and more general. So, mean value theorem still has criteria, still has to be continuous on the closed, differentiable on the open. Hey, do you guys notice that both of them have the same first two? Okay, why is it continuous on the closed? Because the endpoints need to be filled. Continuous on the closed, the endpoints need to be filled. So continuous, brackets. This is where kids have a lot of struggle with memorizing. Differentiable on the open, why? Because I need in between to be no sharp points or vertical tangent lines. Okay? So I have continuous on the closed, differentiable on the open, then there must be, I want you guys to really quickly change the to at least one. I know, I do apologize. You can use a cool little carrot though, do the proofreading. Proofreading or editing notation. I want you guys to say then there is at least one. We're not saying as in only one. We're saying at least one, and guess what? I know, I'm sorry, I apologize. I didn't catch it yesterday. I want you to go pick out the I know, I do apologize. But use your cool editing.
It's not cool. Your notes look ugly.
No, they don't.
See, Misty, it's not me.
I know. I do feel a struggle. I would be inwardly sighing as well. Okay, the sigh is over.
That's just the inward sigh. Okay, not an outward sigh.
It's okay, it's morning, right? So there's at least one. So both of them guarantee something. Roles only guarantees a zero. MBT guarantees all the average rates for any A and B. The average rates. Still specific, and yet not as specific as roles. Now, here we go. We're going to actually start with examples on MBT. Because I was mentioning just a second ago, if you guys caught it, On the AP, you can always use MVT when needing to defend the existence of a derivative given certain conditions. You can always use MVT, you can't always use roles. So we're going to cover MVT first, and then I have some roles examples on the next page, and we'll say, hey, could we use the roles theorem? Yeah. Could we use MVT? Yeah. Oh, okay. So first of all, we have to determine whether MVT applies. So we have to check two conditions. I'm just going to write them here. You guys have them up above. You don't necessarily need to write them if you don't want to. I'm just going to write what they need to be. If function is continuous on the closed interval, if a function is differentiable on the open interval, those are the two conditions. Those are the two ifs. Those are the two that need to be met first. And if that's true, these are our ifs, then we get to say f prime of c is equal to f of b being the second endpoint minus f of a being the first endpoint, b minus a, and that's for some c within the open interval a to b. A to b. Okay. Number one, can you guys visualize the graph of the cubic? Just generally the curve. What's the cubic function look like? Zip. Ish, right? Okay, is it continuous?
Yes.
Anywhere and everywhere as long as it keeps going?
Yeah.
Oh, cool. All right, so number one, you didn't have to do any math, just say continuous. On -1 to 2. Check. If it's discontinuous, well, we'll talk about how it shows up, but it's a polynomial. He's fine. He's continuous everywhere. No denominator, no square roots, no ln's, no trig. He's fine. Number two. Ooh, no piecewise function. Number two, differentiable. Well, to figure out differentiability, shouldn't we take the derivative? Maybe we need it anyway. Okay, who's the derivative?
X squared plus 1.
3x squared plus 1. You guys tracking on the power rule? Cool. Visualize the derivative. It's just a parabola. Is the derivative continuous? Yes. Oh, cool. If the derivative is continuous, if he's existing everywhere, then what's that mean about the differentiability?
Good.
Now notice, I said if the derivative is continuous. I didn't say the original. If the derivative is continuous and no crazy domain things going on, yeah, things can be differentiable. So, determine whether MVT applies. It does! So we can say, since f is, number one, continuous, number two, differentiable, continuous on the closed, differentiable on the open, then we can state MVT applies, which says there is at least one C within, what would be the interval on this one?
-1.
Open interval, somewhere in between. There's at least one C within -1 to 2, such that, you can use it ST, it's a lot easier, such that f prime of C equals, well, wait, we gotta plug in stuff, right? So it'd be f of who?
2.
F of B, good, which is the second one, 2. Minus f of A, which is the first one, all over B minus A. Good. Now guys, what do the directions say? The directions say figure out whether or not MVT applies. We did!
So we don't need to find.
So we can say da-da-da-da-da-da-da, but then it says find the C values. Oh, okay, we have to find the C's within -1 to 2 such that that is true. What do we do? Plug in. Now pause. Does it make sense we're plugging into a -1 to F? Okay. I'm not going to take a long time on that. If we do plug in 2, that's 8 plus 2 is 10, 10 minus 4 is, so that's F of 2. Plugging in -1. -1 minus 1, -2 minus 4, -6. All over 2 minus -1 would be 2 plus 1 or 3. Guys, hopefully you see we're plugging in on the right with function notation plugging into F. And we're going to simplify, but what should go on the left?
3x squared plus 1.
The derivative. All this changes, they just say, whatever, call him C. Call who C? The x value. Oh, okay, so 3c squared plus 1. Solve. What a lot of people get mixed up when they're going really fast is they know to plug in over here. They've been doing something like that since Algebra 2, pre-cal, maybe even Algebra 1. They've been plugging in to a function. But a lot of people forget to plug in the derivative. So if we were to solve over here, 6, that's 12 over 3 is 4, right? Guess what one of the multiple choice answers would be? 4. But it's not right. I'm not solving for 4. I'm solving for C, and I have to set the derivative equal to 4. So now I just plug and chug. Well, I already plugged and chugged. Now I just solve. Subtract the 1. Divide by 3. Oh, careful, subtract. 4 minus 1, 3, right? C squared is equal to plus or minus 1, right? Divide by 3. Plus or minus 1 is square root. However, why?
It's just C equals plus 1.
Yeah, because I have to think about which of these C's, oh, sorry. I did not square root, not C squared, C. Both same. C is equal to plus or minus 1. However, I need to think about within negative 1 to 2, who gets canceled out? C only equals positive 1. That's the only one that's guaranteed by the theorem. It's true that C could equal plus or minus 1 in just some normal general problem, but if we're using MBT, it has to be in between, so we don't use negative 1, we only use positive. Done. I'm going to start you guys on number 2, but I'm going to have you finish the plugging in stuff on your own, and we'll see if you get there.
Shoot.
But let's start together with the since, because this is kind of tricky. What do you guys think about the continuous? Why not?
No, maybe because if x equals 0, then
Is not continuous at x equals 0, which is within negative 1 to 2. We don't have to go any further, right? If we have a not right away, MBT does not, so we stop. Because if we're supposed to find C is guaranteed by the theorem doesn't apply, so we have nothing guaranteed by the theorem. The theorem only works if the function is continuous on the closed, differentiable on the open. Kiddos, what does this graph look like? Does anybody actually know?
might it be like a
A foomp and a foomp? We do have a vertical asymptote.
two
Where's the vertical asymptote at?
is it a
Is there also a
That's zero.
horizontal asymptote at
So-
positive 1 or
If
maybe
it's-
negative 1?
Yes, I know it's vertical and not a whole because holes cancel. And x
Is it-
plus 1 and x can't reduce.
is it 0
So that's a vertical asymptote. Tyler's saying there's a horizontal because he's done the degree test. And the degree is high, so it does have a horizontal at 1.
There's also 0 at
Yeah, so it's
Negative.
just-
Ooh, now we're thinking
an L shape
intercepts.
in the top
When
left.
x is negative 1, it's going to be at 0. Is it going to be a